mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Good morning, physics class. It's good to be back today. Yesterday you had an assignment that dealt with some electric forces, and we're going to go over some of those examples on the board behind me in just a couple of minutes. But I just want to welcome you back to another day. We are on Wednesday, getting ready, heading in toward the Easter weekend, and looking forward to that, as different as it will be. As we get rolling today, I do again want to start with a verse of the day. And so today's verse comes from Psalm 30. It's two verses, Psalm 30, verses 4 and 5. And they say, "Sing to the Lord, you saints of his, praise his holy name. For his anger lasts only a moment, but his favor lasts a lifetime. Weeping may remain for a night, but rejoicing comes in the morning." And so again, as we head into Easter weekend, remember that, that there might be weeping for a time, but joy will come, and God's favor lasts a lifetime. It's a good reminder to remember that God takes the long view of things. In our lives, we're tempted to look at short-term things, but God has the entire eternity within his view, and he sees the long picture of things. And as we talked about earlier, any expectations we have, he will exceed those, because again, he sees the whole picture from beginning to end, and he is timeless, and he has eternity in his mind, and so we too can have that eternity in our mind as well. All right, let's turn our attention to a little bit of physics. On the board behind me, I have a question. I have a question number 4 on the board here that I have worked through, and I want to walk through it with you. And then we'll do question 5 as well. These are the hardest two because, again, they dealt with net electric fields, and when we're dealing with anything that is a net force, field, etc., it is the sum of all the forces, all the fields that are acting in a particular spot. And so in this question, we had 2 charged particles. We had a positively charged particle here at x, a negatively charged particle here at y, and we were asked to find the direction and magnitude of the electric field at point z. We had our distances. It was 0.45 meters between x and y, and 0.3 meters between y and z. So when we are finding a net electric field, again, we have to find the individual fields. So first thing we're going to do is we're going to ignore y and just look at the field from x to z. And to do that, we set up our formula. Electric field from x to z is kq over r squared. We plug in our numbers, we use our calculators, we get 8.0 times 10 to the 5 newtons per coulomb. Now it is in the right direction because, again, this particle is positively charged. When we test fields, we use a positive charge. Positive charges repel each other, so the field would be in that direction to the right. All right. Secondly, then, we ignore x, and we find the field from y to z. So electric field from y to z, same formula. Fill in the formula with our numbers. The only thing that changes is we change the q to what the charge on y is. We change the distance from 0.75, which is from x to z. We change that to 0.3 meters from y to z. And we get 1 times 10 to the 6 newtons per coulomb, and that's going to be left. Again, now this is a negative charge. Our test particle here is positive. It's going to be attracted to y, and it is to the left. All right, now find the electric field net. It's the sum of those 2 fields. We take the one that's to the right plus the one that's to the left as a negative number because it's the other direction. We get a negative answer of -2 times 10 to the 5 newtons per coulomb, and because it's negative, we know it's left. If you're doing this, please don't write down the negative sign, and left, one or the other will suffice. Okay, so again, it's important to find the individual fields and then find the sum of those individual fields to find the net field. All right, let's go do question 5 on the other board. So Question 5 was a similar type of question, except it wasn't in a straight line. Okay, same question. Find the net magnetic or the net electric field at point Z. Okay, but now it put X and Y at the corners of a triangle. All right, it gave us some distances. It told us that the height of this triangle was 4 centimeters or 0.4 meters. The distance from the corner to the middle was 0.03 meters, 3 centimeters it said in the question, which means we can find this hypotenuse, we can find this side, again use Pythagoras' theorem, and it would be 0.05 meters. Okay, so I didn't do that calculation for you. It's a 3, 4, 5 triangle. All right, so now again, what we're going to do is we're going to first find the individual electric fields. So from X to Z, what is the electric field? From Y to Z, what is the electric field? And hopefully you can already see that those two numbers should be the same, because the charged particles have the same charge, the distance between them is the same. So here's my calculation. The electric field from X to Z could also be from Y to Z. Okay, Q over R squared, put in our numbers, we get 7.2 times 10 to the 4 newtons per coulomb. All right, so those are our two individual electric fields. Okay, so both of these here are 7.2 times 10 to the 4 newtons per coulomb. Now, when we add them, we want to add them together. We want to do the same thing we did on the other board, where we want to add these two fields together, but because they're not in a straight line, we have to add them as vectors. So I've done that over here, and hopefully you can see it, but listen to what I say. I've drawn our triangle here in black. Okay, 0.3, 0.5, or 0.03, 0.05, 0.04, and I've drawn the line down the middle. That allows me to find this angle of 37 degrees. All right, if I've got 3 sides of a triangle, it's a right triangle, we can find this angle. So a number of different ways. Use any one of the 3 trig ratios. I think when I did it, I did tan theta equals 0.03 over 0.04, and I was able to find this theta of 37 degrees. All right. So if I draw this line straight up here, okay, the height line, this diagonal, this dashed line straight up, that's going to tell me that both of these angles are also 37. All right, because cutting it straight in half, these lines are continuous, and we're going to get a 37-degree angle. So now over here, I've drawn these two lines, I've drawn them tip to tail, which means I've taken this vector here, and instead of drawing it there, I've drawn it here. Okay, so that's here. So I've got the first vector, this would be EXZ, and this one here would be EYZ. Right? Okay, I've just drawn them so that they are tip to tail. Right here, tip to tail. All right. Okay, so we get this triangle. Because this angle was 37, that's not going to change as we move it over here, right? The angle between our vector and this vertical line that we've drawn, this dashed line, is 37. It stays 37. It's an isosceles triangle because both EXZ and EYZ are the same value, so that means this top angle is 37, and that means we can find this angle of 106 degrees by doing 180 minus 37 minus 37. All right, so that gives us this triangle. All we need to do now is we need to find E net. So to do that, we're going to go back to our trigonometry. This is no longer a right triangle, so we can't use right angle trigonometry. We're going to use sine law. And in sine law, we take E net over the sine of 106 degrees. We make that equal to one of the sides over the sine of the angle opposite it. So 7.2 times 10 to the 4 over the sine of 37. And we'll plunge this into our calculator, and you will get an answer of 1.2 times 10 to the 5 newtons per coulomb. And as you can see from our diagram, that will be going straight up. Hope that makes some sense. Again, the process is the same in terms of finding the individual electric fields and then to find the sum of them. Okay, now when it's not in straight lines, we have to add vectors. And to add vectors, place them tip to tail. The angles are where it gets a little fun to find in here. Okay, but again, if you draw the diagram, you should be able to see it reasonably easily. All right, so that's it for today. I'm not going to give you any new content that I'm going to give you on the whiteboard today, but I am going to give you a reading out of your textbook. We're going to move into magnetic fields for a few days now, and then before we get into combining the two together into what's called electromagnetism. So today, for your lesson today, what I'm going to get you to do is read a little bit out of your textbook on magnetism and some magnetism properties, and then do just a couple of questions out of your textbook. And so you can find the section and page numbers out of your textbook that you need to read on Connect. So check Connect for that. The assignment, the reading, and the questions will be there. And it should be fairly quick and straightforward today. Have a great day, and we will see you tomorrow.